And welcome back to College Algebra. I am Paul Walcher, and this will be our set of videos for section P8. As we finish off chapter P, I think you'll actually like P8 quite a bit better than several of the previous sections. There are still some difficult things in it, but on the whole I would think it's quite a bit easier to deal with than a lot of the things in P7, P6, P5, and P4. In P8, we are solving basic equations. We've already done a tiny bit of this in the context of other problems, but here's our first real introduction to solving equations. And of course, we're going to be doing this all semester, because as anybody who's ever taken an algebra class will tell you, solving equations is a big part of the course. So first, some initial definitions. What is an equation? Here's a fairly typical definition. Statement that two mathematical expressions are equal. So here I have an expression equal another expression. Here is one with no variables, but it's still true. One on this side, one on this side. Equations are just going to be our tool for solving real-world problems. In college algebra, we're still probably going to have idealized real-world problems to a certain extent, and you can't really escape that since you use mathematics to model the real world. You don't. The real world does work mathematically, but there's so many variables it's almost impossible to keep track of, so you have to narrow it down at some point. But still, even with idealized situations, you can still use math as a good predictor. It gives you a good rule of thumb to work by. So we're going to use equations to solve a lot of application problems. And most of the equations we're going to look at are going to be equations more like this, that have variables in them. And the variables are just symbols that stand for numbers. I think we've already introduced the term before in P5. To solve an equation, you have to find the value of the variable that makes the equation true. So that can be as simple as looking at it and saying, well, the number you add to 2 to get 7 is 5. You just did a subtraction. But we'll establish a set of steps to follow in general if you want to solve an equation. Because there's several things you can do to equations to help you come up with the set of solutions, the set of values that x can take if the equation is going to be equal. Because sometimes it can be 1, like in this case, but there could be equations where you'll have several solutions. Or no solutions. Alright. As we said, the process of finding all those solutions is called solving. In fact, it's worth mentioning, sometimes, I think I actually already said it back, well, I don't know which section ago. There are kind of two problems in mathematics, solving equations and simplifying expressions. Solving equations often has simplifying inside it. Simplifying, you're just rewriting something, so the number you start with is the number you end with. Solving equations is all about manipulating an equation so you come down to a certain form, x equals. So you have a lot more freedom with the thing you can do to equations than the thing you can do in just simplifying. Because here's kind of the process we will go through to solve equations. You start with an equation, and then you come up with a set of what is called equivalent equations until you break it down to a really simple equivalent equation, x equals something. So when we're solving an equation, we're just going to follow a series of equivalent equations down to a very simple one, x equals. Sometimes we'll end up with a different looking result than this, and that'll give us other kinds of solutions, other kinds of results, I should say, and we'll look at that as it happens. So here's how we're going to be solving equations, how we're going to be generating these equivalent equations. We have two solving principles, or properties. They are called the addition principle and the multiplication principle. The first one, you can see right here, this symbol right here means if and only if, or is equivalent to. So A equals B if and only if A plus C equals B plus C. So that means if you have an equation like x plus 3, actually let's start off with x minus 2 equal 3, you can add something to both sides of the equation, and the equation will still be true. Now I have x minus 2 plus 2 equal 3 plus 2, and then you can simplify and get x equal 5. Now I can also do subtraction, because if I wanted to get rid of a positive number like this, I can subtract, because subtracting 2 is the same thing as adding a negative. Since I can do this with any real numbers, that means I can do subtraction just as well as addition. I don't need a subtraction principle. Similarly, you can multiply something into both sides of an equation. So if I had x over 2 equal 3, I can multiply both sides by 2. I get x equals 6. I can also divide something into both sides, because dividing by something is, as we've said many times, the same thing as multiplying by the reciprocal. So I don't need a division principle either, because the multiplication principle takes care of it. So our two properties say if we're given an equation, we can add or subtract the same thing to both sides of the equation, and the equation will still be true. We'll get an equivalent equation. And we can also multiply and divide numbers into both sides. So we are going to start solving some equations soon, and you're already probably familiar with the process, so you can probably skip ahead if you want. I'm just going to list out some general steps we take in a bit. The first set of equations we're going to be solving are linear equations, or at least equations that lead to linear equations. And a linear equation in one variable is just an equation that's equivalent to that form, ax plus b equals 0. A and b are real numbers, x is a variable. The key point there is that x has a power of 1. So ax squared plus b would not be linear. If you just have an equation with x to a single power, your process for solving the equation is always going to be the same. That's actually handy to know, because if you recognize the form of the equation, you'll often be able to tell from that form how you should go about solving it. And you won't need to get stuck, thinking about, okay, how do I approach this? It's just down to the form of the equation. If you only have x to a single power, no matter how many other variables you have or numbers you have, it's always going to be the same process, and we'll talk about that in the examples. So here's just a table from the book, just kind of a drilling on recognizing linear and nonlinear equations. These are all linear because, as you see, when x appears, it has at most a power. It has only a power of 1. This is nonlinear. It has 2 powers of x, but what makes it not linear is this x squared. Oh, it didn't actually show up here. I don't actually remember what the full equation was, but I could just make one up. It had a square root x in it. So that's why it wasn't linear because it's 3 divided by x, not just, so that's like x to the negative 1. It doesn't have just x to the 1. So our process to solve linear equations is that we simplify both sides of the equation, and that may involve several things. We might have to remove parentheses, we might have to collect like terms, we'll probably have to do that. We might have to clear fractions or decimals. That's sometimes optional, sometimes not. Generally that's optional when you're solving linear equations, but this could also be considered to solve basic equations. Because we'll see some other equations that aren't technically linear that will still basically follow this process. Once you've simplified both sides, you want to use the addition principle to move all terms with the variable you're solving for to one side, either the left or the right, and then move all the other terms to the opposite side. So if you got x plus 2 equal 3, you want to move that 2 over to the opposite side. So all your variable terms will be on a single side. And then you might have to collect like terms again. Then lastly, you might have some, if x is your variable, you might have some number in front of your variable then, like 3x or 7x or whatever. At that point you want to use the multiplication principle to divide that out. And then finally we'll check at the end. There are 3 possible results we'll get from doing these equation solvings. We could end up with a finite number of solutions. That's what we'll get most of the time. Equations that have a finite number of solutions are called conditional. And that's just the typical ones we'll be seeing. We'll solve them. We'll get x equals something specific. You could have an infinite number of solutions. Happens from time to time. Those happen when you have equations that are called identities. Here's an example of one. This is true no matter what value x takes. You know, if x is 1, it'll be true. If x is 2, this will be true. If x is negative 7, this will be true. No matter what number it is, a number plus 3 equals the same number plus 3. And it's always true. And if you try to get all your variables on the same side, you just end up with 3 equal 3. Always true. That's true for every real number. So that will be your solution if you have to give the solution set. There's an infinite number of solutions, and it is all real numbers. That specific set of solutions is all real numbers. Sometimes you might have to rule out a single point or two, but it's still going to be all real numbers except maybe a couple points. And some equations have no solution. Those equations are called contradictions, and here's an example down here. No number when you add 3 is equal to the same number plus 4. It's just impossible. And if you subtracted the x from both sides, you'd end up with something that's obviously not true. 3 equals 4. 3 does never equal 4, so it's impossible for that equation to have a solution. So the result of solving that equation is the conclusion that there is no solution. Sometimes you just say no solution. Sometimes it asks what's the solution set, and for that you'd say the empty set. Been a while since we've seen this symbol, but that's what it stands for. I think I will end this first video here, and we'll start up the next one with some examples. We may end this section in 2 videos. We'll see.